I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to our new episode of Physics Matter monthly online and live colloquium series. So it has been already now 4 years since we have kick-started this series dedicated to physics for development and initiated by Luisa Cifarelli, who is here, and with Paola Catapano using the Polo Quest as the first vehicle. So our scientific expedition and colloquia highlight the capability of major research infrastructure like CERN and Sesame to foster physics spin-off. So explore our rich portfolio of recording public lecture, expedition, and embark on the journey through this fascinating universe where physics matters. So in the recent months, we have focused on showing how physics can tackle global health challenge by exploring, for instance, the boron neutron capture therapy, live from Japan, with Dr. Iguaya. And earlier, we have also fixtures, Dr. Dawson and Damanovic as well, highlighting physics potential to combat cancer. And today, this is not only 4 years that we are celebrating, but 70 years of the experience as well, the broad experience and the existence of CERN. So in our panel today, we have the honor also to have with us the initiatrice of this Physics Matter with Lisa Cifarelli, who is from Bologna University, and Alan Hurt, from Los Alamos, who, like me, are former chairs of the Forum of International Physics, the FIP, at the American Physical Society, supporting this event. So my name is Christine Dove, and I'm the engineering scientist at the European Spallation Source in Sweden, and also the current chair for the IUPAP Working Group on Particle Accelerator for Science and Society. But most important with us today, we have our esteemed invited speaker, Dr. Luciano Musa, who is the main coordinator for the CERN 70th anniversary celebration. So it's really a great honor to have you with us, and you have been a distinguished career in particle physics, which has begun with your contribution in the NA48 experiment at CERN, during your PhD and your postgraduate work at the INFN in Italy, where you have been studying CP violation. So in 1997, you have joined the ALICE experiment at CERN for the LHC, playing a pivotal role in the development of its front end and readout electronics, particularly for the time projection chamber. And as the project leader, for the ALICE time tracking system, in 2011, you have oversaw your graduated work with the collaboration, becoming the spokesperson of the ALICE collaboration from 2020 to 2022. And currently, you lead the CERN ALICE team, focusing on physics research and innovative detector technology. But beyond ALICE as well, Dr. Musa have been making a lot of significant contribution to other CERN experiments, including Obelix, the NA45, and detector studies for the International Linear Collider. Throughout your career, you have published more than 500 papers and mentioned and mentored more than 30 different PhD students, leaving then a long-lasting impact in the field of high-energy physics. So we are really happy to have you here. And so while we will keep maybe the question and answer for the end of your talk, so the people can start writing them the questions in the question and answer, and we can also give you the possibility to speak and address directly to our panelists your question after your 40 minutes presentation. So Dr. Musa, so the floor or the screen is yours.
Hello, everyone, and thank you very much, Christine, for the kind introduction and the invitation to speak about CERN and its first 70 years. So this really represents a fascinating and important milestone and a fascinating journey through science, innovation, and but much more than that, also international collaboration and 70 years of open and inclusive science. So let me share my my screen. I hope you can see. Not yet.
There we go.
And okay, now it should be okay.
Looks good.
Right, and yes, as you said, Christine, the 2024 marks the 70th anniversary of CERN's foundation. The official birth date is the 29th September 1954. Really an important milestone which we have celebrated with events at CERN, but also across the entire community with more than 120 events with different formats addressing also different audiences organized literally across the world, mostly in CERN's member and associated member states, but you know, within across the entire CERN community. Now, CERN's history is filled with numerous milestones and achievements, and it is always difficult to highlight a few of them. And so, for obvious time reasons, I've I selected a few and left out many other important milestones that would be that marked this 70 years of history of CERN. Now, the CERN journey begins in the late 1940s, early 1950s. Let me put this in context. We are obviously after World War II. European science was no longer world class. And there was a strong desire to rebuild European science and promote collaborations between countries that were struggling to recover from the war, from a devastating war. And Louis de Broglie was the one to put forward the first official proposal for the creation of a European laboratory during the European Cultural Conference, which was held in Lausanne in December 1949. So this was a group of visionary scientists and not only scientists, also diplomats that imagined creating a European atomic physics laboratory. The idea was that such a laboratory would not only allow the European scientists to work together and restore also scientific excellence and prevent further brain drain or even reverse brain drain, but also allow them to share the already high and growing cost of nuclear physics facilities. And it's quite interesting to read, I will do that for you, a quote from the first official proposal by Louis de Broglie, where he said, the creation of a laboratory or institution where it would be possible to do scientific work, but somehow beyond the framework of the different participating states, endowed with more resources than national facilities. Such a laboratory could undertake tasks which by virtue and their size and cost were beyond the scope of individual countries. So this is an important element of the vision of the founding fathers of CERN. Now, a very important figure in that process was Isidor Rabi, Nobel laureate, who had a very important role within UNESCO. By the way, UNESCO was created in 1945, so it was also a very young international organization. And Isidor Rabi was crucial in advocating the need for the establishment of an international research laboratory, or actually for the need of international research laboratories in general. And his vision for science as a unifying force in a post-war significantly shaped the landscape of the international scientific collaborations. And CERN somehow was culminating this vision. And Rabi, along with other scientists and diplomats, pushed for the creation of a large-scale pan-European scientific research facility. And a very important step was the meeting of UNESCO in Paris in December 1951, where the first resolution concerning the establishment of a European Council for Nuclear Research was adopted. And 2 months later, so we are then in February 1952, 11 countries signed an agreement establishing the Provisional Council. So this was the Conseil Européen pour la Recherche Nucléaire. So the acronym CERN was born. Edoardo Amaldi was made Secretary General of the Provisional CERN Council. Now, the CERN Convention, after this establishment of this provisional organization or council, they've been working on the preparation of a convention. This took about 15 months, and it was established in July 1953 and was ratified by 12 founding member states. Belgium, Denmark, France, the Federal Republic of Germany, Greece, Italy, the Netherlands, Norway, Sweden, Switzerland, the UK, and Yugoslavia. It's also very interesting to note the presence of Yugoslavia among the first group of 12 countries that participated in the foundation of CERN. It took another 12-13 months to have such a convention ratified by the parliaments of these 12 countries. And on the 29th September 1954, the European Organization for Nuclear Research officially came into being. So the Conseil Européen pour la Recherche Nucléaire was dissolved, but the acronym CERN remained to refer to the Organization for Nuclear, the European Organization for Nuclear Research. So that's really a bit of history on the process that led to the foundation of CERN. And within a few years, CERN brought constructed the first accelerator and brought into operation the first accelerator, the synchrocyclotron, and shortly after the proton synchrotron, and enabling a pioneering research within a few years from its foundation. Now, before moving to a few scientific highlights, I just wanted to remark that CERN's founding fathers would be very proud of what CERN has become today, an international organization at the global scale, comprising 24 member states, 10 associated member states, and also a vast and diverse scientific community representing over 110 nationalities from around the world. And as I mentioned before, CERN is not only a scientific and enterprise. Technology innovation is at the heart of what we do, but also the other core values are really at the basis of what CERN is today. In particular, the international collaboration, which I've tried to highlight, but there is much more, and in particular, the open science, the openness, the sharing of the results and the knowledge that is acquired through our experiments at CERN with the rest of the world. And let me outline that this is actually cast into the convention. So in the CERN Constitution. So now let me move forward and start talking about the let's say scientific achievements that have marked this first 7 decades, and which are inextricably tied to its unique accelerator complex. Since its inception in 1954, CERN has built particle accelerators at higher and higher energies, accelerating mostly hadron beams, protons, and also nuclei, as we will see, but also electron and positron beams. So from the synchrotron, which entered in operation in 1957, accelerating a proton beam at energies of 600 MeV, to the proton synchrotron, the PS, which began operation in 1959, accelerating protons to an energy of 28 GeV. The PS, by the way, was CERN's first large accelerator and has been a workhorse of the laboratory, contributing to numerous important discoveries, as we'll be seeing in a moment, and also serving as an injector for higher energy accelerators. Then the ISR, the intersecting storage rings, which was CERN's first large, which was the first collider that began operation in 1971, was the first proton-proton collider. It collided the protons to energies of up to 62 GeV, center of mass energy. Then the superproton synchrotron, which began operation in 1976, a very versatile particle accelerator and very powerful, with a circumference of 7 kilometers and capable of accelerating protons to an energy of 450 GeV. I will show also that this has been modified actually in 1980 to be used as a proton-antiproton collider, which enabled the discovery of the W and Z bosons in 1983. The LEP, the Large Electron Positron Collider at CERN, was one of the largest and most powerful particle accelerators ever built, most complex ones. And it operated from 1989 to 2000 in the 27-kilometer circular tunnel, which it is now the home to the Large Hadron Collider, and which is presently our flagship accelerator, and it's the largest and the most powerful accelerator in the world. Now let me start with the first scientific achievement, and I'd like to mention this because for several reasons, but the main one is that it really shows how within 2 or 3 years a machine was brought into operation, and first important scientific results were achieved, also reflecting very motivated and ingenious scientific community since the very beginning. This is the discovery of the rare pion decay. So the decay of the pion in an electron and an electron neutrino, which was a very rare process, respected to the decay into muon and muon neutrino. Most of 99.9% of the times, that's the decay process. And 10 to the minus 4 times, it decays into an electron and neutrino. And this discovery was more than just, the first discovery at CERN. It was also a crucial verification of the weak force as a vector axial coupling. And a confirmation of the emerging electroweak theory. So a very important experimental result. And this measured ratio, which you see here, was indeed a significant piece of evidence that was supporting the emerging electroweak theory. Continuing in 1959, the CERN proton synchrotron began operation, producing a 24 GeV proton beam, and for a time actually holding the title of the highest energy accelerator in the world. And it marked the CERN's entry into the so-called high energy neutrino beam era, which paved the way to some of the most important discoveries in particle physics. One of the most significant ones was the discovery of the neutral currents in 1973, observed by the Gargamel bubble chamber. So this massive detector that you see in the picture here, filled with heavy liquid freon. So this is a 2 meter of diameter and nearly 5 meters long, 1,000 tons of liquid freon, which enabled the detection of events involving neutrinos interacting with electrons through the exchange of Z0 bosons, so through neutral current interaction, as in the event that you see here in this diagram. And now you see here one of the important events recorded, where you see the knocked out electron produced, which is produced, leaves in the bubble chamber a visible trail of bubble, which is then recorded in the detector. And this trail is characteristics of an electron because of its energy loss and scattering behavior. Now, the observation of neutral currents was a very important achievement, as it really established on firm grounds the validity of the electroweak theory as a key component of the standard model. And also, let me add that this discovery certainly solidified also CERN's role as a leader in high energy physics, as playing an important role, a leading role in the field. But the PS and the Gargamel also provided many more contributions. PS has been a really very important machine, contributions to the development of for instance, of the quark model, and also an indirect evidence of their fractional charge. So there were all these scattering experiments which provided support for the quark model through the observation of patterns of hadronic resonances. So through the hadronic spectroscopy, such as their organization into multiplets, which were predicted by the SU3 symmetry. But also helps identifying properties of hadrons, as the spin, parity, charge, and their interaction dynamics. Of course, these were not experiments aiming at probing the structure of hadrons as it would have been done later at higher energies in the deep inelastic scattering experiments. Now, let me also outline, this is a very important point, that actually the combined measurement of neutral and charged currents using neutrino and antineutrino beams, so this R and R bar, also provided, let's say, a first indication of the mass of the W and Z bosons. And the estimated mass of the W boson derived from this experiment was remarkably close to the actual value later confirmed. So what was estimated was 70 GeV. And these findings were pivotal in also indicating the way forward, in which region one had to look really to have a direct observation of the W and Z bosons, which then happened a decade after. And again, also this was a very important achievement, as already mentioned, in cementing CERN's role at the forefront of particle physics. Now, the bubble and spark chambers that, as shown now, the Gargamel, but this was the period where essentially particle detection was done by using indeed mostly bubble chambers, spark chambers, and then taking photographs of the events. And this was severely limiting the rate capabilities of those experiments. And meanwhile, in 1968, George Charpak revolutionized particle detection with the invention of the multi-wire proportional chamber, marking the beginning of a new era of electronic particle detectors. And also, by the way, they are used in medicine for medical imaging. And as I said before, this very important innovation, particle detection, was done through photographs from bubble chambers and sparking chambers, which not only was limiting the rate capabilities, but also was involved in a very laborious process for the reconstruction of the events. Now, the multi-wire proportional chambers, which essentially a gas-filled enclosure with many parallel wires connected each to an individual amplifier. And what happens is that then when a charged particle traverses the chamber, it ionizes the gas, liberating an electron and ions, which then the electrons will travel towards the anode wires. And when they are in the proximity, then they create an avalanche process, inducing an electronic pulse into the wire, which then is processed with a standard electronic channel and eventually processed digitally in a computer. And that really literally revolutionized the way of doing particle physics experiments. And for this transformative invention, Charpak was awarded the Nobel Prize in 1992. And as I mentioned, beyond its impact in particle physics, which, for instance, was also instrumental to the discovery of the W and Z boson, this invention has also found plenty of applications in medicine, biology, and security. Now, let me now move to the ISR, the intersecting storage ring, which was the world's first hadron collider, and which began operations in the early 1970s. It collided protons at a center of mass energy of up to 62 GeV, a remarkable achievement at the time. Now, the beams intersecting angle, as you can see from this picture here, and the detector's location and also their geometry and design was really optimized to capture the forward-going debris of the from the collision of the interaction, which reflected the understanding at that time. So let's say the pre-QCD understanding, and which obviously turned out not to be optimal to study in particular the physics of the phenomena in the transverse direction. Nevertheless, the ISR was a crucial machine, made significant contributions to the development of quantum chromodynamics, so the theory describing the strong force and the structure of hadrons. And the insights gained here at the ISR were, let's say, complementing the findings from deep inelastic scattering experiments at ZRAC. Now, for instance, let me just mention one example. A major breakthrough from the ISR occurred between 1972 and 1973, when with the observation of an entirely unexpected phenomenon, the production of hadrons at a very large transverse momentum, largely deviating from what was expected to be the exponential fall-off of particle production. And this discovery was a shocking result to the physics community, as it didn't fit the prevailing models at the time. However, this result was not unexpected, since it was consistent with the emerging theory of QCD, which describes protons as being composed of quarks and gluons. And there were also attempts of really interpreting, successful attempts of interpreting these results, indeed, with the Platonic structure of hadrons. And these findings set the stage for future discovery, also confirming the power of QCD as a theoretical framework. Now, building on the success of the ISR, CERN continue to then to push the frontiers, leading to the historic discovery of the W and Z boson in 1983. Which was the culmination of years of research that began, as I've shown, with experiments like those in the Gargamelle bubble chamber, which provided the first hints of neutral currents, and which also, as I mentioned, as I outlined, guided actually the physicists to search in the energy range of 60-90 GeV. And certainly, this is what inspired then Carlo Rubbia in 1976 to propose a very bold idea to modify the superproton synchrotron, which was a single beam accelerator, into a collider of protons and antiprotons. And this innovative approach led to the first proton-antiproton collisions in 1981. With two specialized multipurpose detectors, UA1 and UA2, which were constructed specifically to detect the W and Z bosons through their decays into leptons. And in 1983, indeed, these bosons were discovered. The announcement was done at the beginning of the year in two separate seminars on January 21st and 20th and 21st. So where UA1 and UA2 presented the first results, revealing 6 candidate events that showed high energy electrons and significant missing energy. So that was a strong indicator of the neutrinos and signaling the presence of the elusive W boson. So the W boson was discovered, and just a few months later, then there was also clear evidence of the Z boson, which was presented in this case. Then one would measure the decay into a lepton pair. And so this discovery was so significant that Carlo Rubbia and Simon van der Meer were awarded the 1984 Nobel Prize in Physics for their roles in this groundbreaking experiments. And yes, you see here this picture which captures a moment of triumph, not just for the physicists involved, but actually for the entire field of particle physics, because it marked really the confirmation of a crucial part of the standard model. Now, let me now step back a moment. So in the mid 1970s, the standard model was emerging as a promising framework, but there were significant questions that remained. QCD was gaining acceptance, but the exact number of quark and lepton families was still uncertain. CP violation offered some insight into the quark sector, with the CP violation measured, for instance, in the Kaon system. Yet much remained to be understood, especially concerning leptons. Well, this is still a very big open question. And one of the critical goals was also to confirm indeed the existence of the W and Z bosons with their direct observation, for which there was a clear prediction in terms of the mass. And to make progress, CERN then established a study group in 1976 to explore the possibility of constructing a large electron-positron collider, which would be dedicated to producing and studying these fundamental particles, the W and Z boson. And by 1982, we were very close to the discovery of the W and Z, but the lab was officially approved, and the W and Z were discovered in 1983. At the 1984 ECFA CERN workshop, it was highlighted the potential also for the LHC, which would eventually then share the same 27-kilometer tunnel with the lab, ensuring that CERN remained at the forefront of particle physics research. I just wanted to highlight how the lab LHC was indeed a two-stage program since the very beginning, with the first phase colliding electrons and positrons, and the second phase colliding hadrons. Now here we see images of lab, an engineering and technological marvel, and of the four experiments conducted at the lab, Aleph, Delphi, L3, and Opal. Each detector has its own unique strengths and perspective, and working together to measure the properties of the Z boson and later of the W boson with unprecedented precision. Let me say that the lab has been really the machine that with a series of high precision measurement put the standard model on firm grounds. It started the circulated beams in summer 1989, and this marked the beginning of LAP era. There's been a first phase, LAP 1, where the collider operated at the center of mass energy around 91 GeV, precisely matching the mass of the Z boson. And over 7 years, the lab became a Z factory, was operated as a Z factory, producing millions of Z bosons. And these high precision studies provided indeed essential tests and very precise measurement of many parameters of the standard model. And then in 1996, the lab entered its second phase, where it operated at even higher energies, eventually reaching 209 GeV, and this allowed, for instance, for the production of pairs of W bosons, which also allowed to make many other critical tests of the electroweak sector of the standard model. So really a very important machine. By the way, it's also the machine that allowed to set very tight constraints on, well, at least set a lower limit for the mass of the Higgs. Now, the size of the lab collaboration was many times larger than any previous experiment, and this created the need for a new universal way of exchanging information, essentially, which is what ultimately led to the birth of the World Wide Web, a tool that revolutionized science, well, not just science, but the entire society. So in March 1989, Tim Berners-Lee submitted the first proposal for the World Wide Web, essentially to merge data networks and hypertext, to provide an easy-to-use global information system, making essentially transparent to the users where information is actually located or originated, and also the many different interfaces used to access this information. Now, by the end of 1990, the first web server and browser was up and running. And in 1993, CERN made a very important decision, so essentially to make the source code of the web available on a royalty-free basis. And then this is what really enabled a very rapid boom of the web. By the end of 1994, the web already had 10,000 servers and more than 10 million users. And then you all know how it quickly further developed. Now, I think I have to here really speed up. So I just wanted to say that, of course, much of the focus of CERN has been on colliders, but I just wanted to mention that also the SPS has been also instrumental in making groundbreaking discoveries. One of the most significant achievements, which is also very dear to my heart since I've been working 6 years on that experiment, was the discovery of direct CP violation, while first hints were already with the 3 sigma measurement achieved by the NA31 experiment in the 80s, and then NA48, which followed, then provided a clear measurement with 5, well above actually 5 standard deviations of the direct CP violation. Let me also mention another important achievement, which is also very close to my field of expertise, which is the discovery of the quark-gluon plasma at the SPS. The SPS accelerated the proton beams, but also the nuclei of heavy atoms, and this is what by combining the results of 7 experiments, a picture emerged providing a compelling evidence of the formation of the confined state of matter, the quark-gluon plasma. And then the baton passed to the to RIC at the Brookhaven National Laboratories for a detailed investigation of the QGP. And this is a very active area of research at the LHC nowadays, with all 4 experiments continuing to study the collision of heavy nuclei. Now, the Large Hadron Collider certainly represents the most ambitious and complex scientific project ever undertaken in the field of particle physics. It was approved in 1994. It took over a decade to construct and began operation in 2009. It collides protons and heavy nuclei at very high energies, today reaching 13.6 TeV in the center of mass for proton collisions. It hosts 4 main experiments: ATLAS, CMS, ALICE, and LHCb, each of which focuses on different aspects of high energy physics. ATLAS and CMS are general purpose experiments, detectors designed to explore a wider range of physics, including the search for new particles like the Higgs boson, which was discovered by these 2 experiments. ALICE is dedicated to studying the quark-gluon plasma, while LHCb focuses on understanding the slight differences between matter and antimatter by studying particles known as B mesons, but does much more than that. The LHC is not just a machine; it's also a global collaboration, actually the largest scientific collaborations involving thousands of scientists from all over the world, working together to push the boundaries of knowledge. And well, I can't help mentioning, of course, the crowning achievement of the LHC, which is the discovery of the Higgs boson. The search was a very meticulous process. By the end of 2011, both ATLAS and CMS experiments had seen signs that something was there, but the evidence wasn't yet strong enough to claim a discovery. Then in the summer 2012, everything changed. Both experiments independently observed the Higgs bosons with a significance of 5 sigma, meaning that the chances of being a statistical fluke were incredibly small, and so the announcement was made. And by the end of 2012, the discovery was confirmed, and then the focus shifted really to studying the Higgs boson properties in detail. Now, let me say that the day of the announcement, the 4th of July 2012, will certainly be remembered as an historic day for particle physics, probably for science. And with this announcement done by the spokespersons of ATLAS and CMS, Fabiola Gianotti and Joan Candela, respectively, in an auditorium which was fully packed. This discovery was really the final piece of the puzzle needed to confirm and complete the standard model. And this, of course, was not only a great success for experimental physics, but also, and especially for the theoretical, and also for theoretical physicists, who had predicted the existence of the Higgs boson nearly half-century earlier. And indeed, in recognition of their pioneering work, Francois Engler and Peter Higgs were awarded the 2013 Nobel Prize in physics. Okay, now let me say that in its long and rich history, CERN has achieved many important technology and technological advancement in these 3 key areas: particle accelerators, particle detectors, and computing, which characterize the different phases of a particle physics experimentation. Now, I did not have the time to include here, we just mentioned before 2 examples, some of the very important technology innovations awarded, achieved at CERN, by, I would say, by the CERN community at large. And but you have then in the backup set of slides which highlight some of the most important achievements, again, a selection, representatives of the different areas. And of course, I would be very happy to get back to that during the discussion. And so let me conclude by saying that so this year we've been celebrating CERN 70th anniversary, looking, of course, back at these 7 decades of important results, discoveries, innovation. Also reflect on the core values, but also it has been an occasion also to continue to look forward with to a future where CERN will continue to explore further into the secrets of the structure of matters and the underlying forces, to the secrets of the universe, and continue to play a pivotal role in scientific exploration, technology innovation, and international collaboration. And yes, I mean, as we symbolically light on the candles of our anniversary cake, this indeed wants to symbolize not just the bright spark of the founding fathers that envision such scientific enterprise, but also the I can say enduring flame of curiosity and collaboration and discovery that continue to animate our community. And I stop there. Thank you for your attention.
So many thanks for this tour of the grand tour, I would say, for this high energy physics or the fundamental particles. So indeed, a lot that we have learned over those short minutes, summarizing those 70 years of amazing progress through CERN. So we will open then the questions box and then try to prepare as well more questions. So we have first, for instance, a question from Sherry, Spencer, who is asking, making a couple of comments. So one, what else was happening in the year 70-72? Then you can answer that. And then also about the reliability of the PS magnet. So going strong after more than 50 years and potentially a question mark. So what do you...
Well, okay, so the 70s, of course, have been a very important decade, and those years have been extremely important for, as I've just shown, the establishment and the consolidation of the the electroweak theory, in particular. Well, I mentioned the discovery of the neutral currents, but also for the building evidence for a partonic structure of hadrons. So there have been many important experiments at different facilities in the world that started providing experimental results that were showing that partons were not simply a mathematical tool to put order in this zoo of particles that were discovered, but had a real physical nature. And in particular, was shown at the ISR this scattering of hadrons at a very large PT. But I see that probably Sherry was referring to something different.
Indeed, because maybe she will speak up, because she has been working there actually also in those years. So, and maybe she wanted to say what she's doing. So I'm going to unmute you. So Sherry, I think it's a perfect way to interact across the Atlantic. So can you join us then now?
Yes, I can. All right, you can't see me. All you can hear is hear me. Okay, so yes. Just wanted to say that I was a graduate student at CERN from 1970 to 1972, doing an experiment. Luciano mentioned that previously mostly it was bubble chambers, and then he skipped to proportional wire chambers. My experiment, which was using a pion beam that the PS could produce, used scintillation counters. So he had kind of skipped over the fact that experiments before the invention of the wire chambers actually mostly used scintillation counters. And so I did an experiment there, bombarding pions into protons, hydrogen target. So just to say that it wasn't that we just went from bubble chambers directly to the wire chambers. And I, of course, was there to hear about Charpak's discovery and invention of the wire chambers, and then to skip to many years later. I eventually became a magnet engineer at SLAC here in California, and I was in charge of designing and building the accelerator magnets for various parts of SLAC, and also at Keck and other places. And I did. It was obvious that the reliability of magnets, accelerator magnets, wasn't as good as it could be. So I surveyed many different laboratories using accelerator magnets, and one of the engineers at CERN filled in my survey for the proton synchrotron magnets. And they were by then they were over 50 years old, and they were still going strong. And if they weren't going strong, then the LHC would not work, because in order to get the protons up to the energies needed that the LHC needs them at, it actually, the whole chain starts way back at the proton synchrotron, or even before the proton synchrotron. Anyway, the fact that LHC continues to run is based on the reliability of 50-year-old or even older now magnets earlier in the chain. And so kudos to the engineers at CERN who designed and built and keep those magnets going. And much of the techniques and the materials that the CERN engineers have used over the years are now repeated in many other accelerator labs all over the world. So you didn't have a chance to talk much about magnets, Luciano, but indeed a very big part of what CERN has given the rest of the world is magnet technology. Thank you very much.
Thank you, Cheryl, for these comments, both actually on the scintillating detectors. Indeed, I also, well, of course, I came a bit later at CERN. Actually, it was my first experience at the CERN was in 1987 as a summer student. But I went through, indeed, and looked at some of the experiments done even before, of course, at the SC and then at the PS. And indeed, scintillating detectors really played a very important role. I was just showing one example. But thank you very much for the remark on the magnets. Indeed, as part of the celebrations for the 70th anniversary, we produce a number of documentary videos. And in one of them, we really tried to highlight the point you just mentioned, that an important contribution that CERN gave was really to the development of the technologies which are the basis of the technologies that are being used today. And you rightly said, I mean, I was showing at the beginning this unique complex of accelerators. And if you look at it, with the exception of SC, which, by the way, stopped operation in the early 90s, all the others are parts of the accelerators that are needed to operate, well, and the ISR, of course, the accelerators that are needed to operate the LHC. And by the way, I'm talking from an office, which is in a building built around the cyclotron, okay, which was stopped, as I said. I don't remember exactly the year, but myself and my team was the first team to actually occupy offices in this building. Okay, thank you, Cheryl, really for these comments.
Indeed, so it was really nice to indeed look at the particles. I saw the detector, but I fully agree that with the magnet also being part as well from the machine team, that we can maybe look in a separate, in another colloquium as well, to develop more on this aspect of those technologies here. And thanks also for this testimony. So this is so important as well to have this contribution from around the world. Many people have been working at CERN, and it's really good to hear you. So we have another question from Sebopa Bertoil, who is asking if you could elaborate on the role of the QCD on the Hadron Colliders. For the QCD, yeah.
The role of the Hadron Colliders to the QCD.
Exactly, to develop a bit on the QCD part, from the theoretical and experimental part.
Yeah, so, well, I mean, as I said, the machines that really contributed significantly to the development of QCD, already the proton synchrotron, and then especially the ISR. I would say both equally. Actually, we had the pleasure of having David Gross at the beginning of this year, who participated in one of the public events, and I spent quite some time with David. And precisely, he was telling me how important the results from the PS and the ISR were to really develop confidence on this partonic the quark model. So, as I mentioned, in the PS was mostly providing studies on the hadron-hadron interaction, so hadron scattering, and also this resonance spectroscopy, and so these results could be interpreted fully and thoroughly only with a quark model, based on the quark model. And the ISR, I think, really brought it. There was even a first evidence of jet production, actually. But certainly the ISR was showing before a plot with really the production of hadrons at a very large PT. And now I don't want to, again, display, it was showing next to it, a plot based, a diagram based on the quark model, which then could interpret correctly the production of hadrons at a large PT. Now, of course, these were not directly probing the structure of hadrons. The compelling evidence and understanding of quarks came with the deep inelastic scattering experiments, of course, at SLAC. And then later also at all the other hadron colliders, well, even at the lab, and then at the other hadron colliders, where then the complete model was then completed with the three families of quarks and etc. and the tevatron.
Thanks a lot for this answer. So we have also a question from Mustafa Mouni, who is asking, so how can we nourish the curiosity to continue the journey of particle physics experiments?
How we can, sorry?
Nourish. So what do you think the future looking at experiment in the field of
Yes.
particle physics?
Yeah. Now, yeah, that's a very good question. Within the community, we hear very often the comment, while in the past, at different stages, there was always a clear objective. Now we're a little bit missing a clear objective, and I find that this is not true. I mean, the discovery of the Higgs opened very important question. The detailed characterization of the Higgs is extremely important, measuring its line shape. The potential shape of the Higgs has even a very important cosmological implications on the stability of the universe. But we should always, of course, keep in mind that the standard model explains many things, but leaves also many questions open. Well, first of all, what we are missing, and is not even attempted by the standard model, is how can I say, a quantum theory of relativity of gravitation. So this is completely missing. But also within the standard model, the unification of the electroweak and the strong force. But we don't understand the standard model, for instance, predicts that we have 3 families of quarks and leptons. But the masses, we can measure the masses with great precision, but we don't understand why they have the values they have, okay, and why 3 families. So there are plenty of open questions. The question of the matter-antimatter symmetry, which remains, of course, we understand the CP violation within the standard model, but that doesn't explain the imbalance between matter and the antimatter, which we measure the universe. And of course, there is the whole question of dark matter and dark energy. Now, what is difficult is that why before we had some hints where to look at, to make progress. It is true that now it's less obvious, but certainly there is awareness, and we are conscious that we have to continue to probe matter at higher energies, so at a smaller and smaller scales, confident that as it happened in the past, this will certainly reveal new phenomena, new processes, which will help us unlocking some of these mysteries. So we should be motivated and conscious that that's the only way we can make progress, by producing new experimental results. And by the way, conscious that fundamental progress in fundamental research is eventually what enables progress of humanity. Okay, in the long term, it's the real motor that enables progress of humanity.
Exactly. So, and we'll come back to that. I think the pure and the applied physics. But we have a question
Can
from
I
Luciano.
just make a comment on this, very, very brief?
Please do so.
Yes, because what Luciano has just said comes back to a fundamental point. If you were an astronomer, you would build a big telescope or space telescope, and you would simply go and explore without thinking beforehand, I will do that because I want to see if this galaxy is green or red, and if it emits lights or light or something else. I mean, the idea is that we have to behave like astronomers. We have the technology to build future powerful instruments and explore, period. We don't really know what we're going to see.
Thank you, Luisa. That's a very a very nice and powerful parallel.
So that's why indeed this is the result. And I really like also all this part maybe that we didn't explore too much, but then through the question or the comment from Susabapa, who was asking the question before, the thing is that the question is for the field of material science as well. So he did his master there, and now he's planning to do to study a PhD at CERN, so on the material science. So focusing on the nano materials, the photonic and so on. And do you have potentially know if it's possible to get an opportunity to further these studies at CERN? So watching and from South Africa, what do you know that this is possible? Maybe we can put as well some of the link for the potential physics career, looking at this material science development. Would you have any recommendation, Luciano? This is in the chat only.
Sorry, I have to admit that I was distracted by reading the question from Khalid. So can you repeat, Christine?
We will put from Savopa, so the link maybe for doing the PhD at CERN, looking at material science.
Sure.
Of applied science. This is the thing that we could develop.
Absolutely. No, it's I mean, this is an important point to outline. Indeed, people who are not familiar with CERN may have the impression that this is a place for particle physicists. It's a real multidisciplinary effort and enterprise where competencies from many different fields, indeed from material science experts to electronics engineers, mechanical engineers, IT engineers, computer specialists, and etc. are needed. And our PhD program, doctoral student program, we can certainly put the links, and also our fellowship program offer really important opportunities for people who are interested in performing their PhD studies and postdoc studies at CERN. And since it was mentioned, for instance, by Cheryl, the relevance of the accelerators, well, you can go through my slides. Once they will be posted, you will see that actually as examples of application of technologies, I was very much focusing on the accelerators, and the progress very much rely on also on material science studies, in particular for the developing of new material, superconductive materials, and our progress in the magnet at present to build stronger and stronger magnets pretty much relies on that. But also, I think Cherry was also hinting to that. When we talk about accelerators, everyone immediately connects this to the very powerful magnets that are needed in the ring. But a very large effort is done for the low energy accelerators. They're starting from the LINAC to the injectors and etc. And these are often those which have large use in everyday life, in particular in medicine, but also in industry, for instance, for ion implants in the semiconductor industry, and many other areas.
I agree that indeed all this application looking at the low energy, so I think it would worth a full session on that. So thanks a lot for mentioning that. On the same line, we have also a question from Diana Valdez, who is asking, so what is the hardest part of physics applied to accelerator? So meaning the programming, so the working with the engineer, or maybe explaining physics in vulgarization talk, for instance, and so on. What is your expectation for the next 10 years in science for the particle accelerator, or speaking to particle accelerator scientists?
Well, I'm not an accelerator physicist myself, so it's a difficult question to answer, and yeah, I would not like to answer that. Certainly, an essential point, for instance, now if we want to go to higher energies, while keeping, of course, these machines within a reasonable size, it's really important to have magnets with larger fields. And so there is an intense R&D activity, which involves also the development of new superconductive materials, maybe also high temperature superconductive materials. But there are many other areas which I'm sure that they are equally important, but it's not really my area of expertise.
But indeed, so we can maybe direct as well to some other presentation we gave, and in the field, indeed, for accelerator with the low temperature, this is where there is a lot of development for the material, for the niobium-13, for instance, and some of those upgrade. And maybe as well to mention with so a comment here from Erkan. So I think it was really nice as well to see. So when CERN was discovering new particles, he mentioned that it was competing against many other centers. So now it seems that CERN is becoming single center. So do you think it is a concern? With Fermilab is still, but no Tevatron. So looking at colliding physics. What do you think?
I think the community has always managed to actually have a variety of experiments, maybe attacking the same problem from different angles, often with completely different facilities. I was mentioning before how progress was made, for instance, in QCD, in the QCD sector, with hadron colliders, but definitely with the deep inelastic scattering experiments. But let me say, if now the community is working on the really very high energy frontier at CERN. So this is always done by having several experiments, again, using different techniques and technologies in a way, but really in a very positive, with a very positive connotations, and this in competition between them. And that is extremely important also to build the confidence on the results. Having said so, of course, it would be problematic if particle physics would be studied only in a single center. And that's why, at least this is now really my very personal view, because we're extremely happy about the ESC program in the United States, but also on the low energy side, the program that FAIR is preparing for studying indeed QCD matter and also hadronic structure, the hadronic physics, and at FAIR with the FAIR facility. And then we are aware of the plans in other areas in Japan and also proposals from China for building an electron-positron collider. All this is extremely important indeed, yes.
So indeed, and now maybe to the question then of Khalid Gore. So looking at those limits, so his comment is as well that if we keep upgrading the energy and the luminosity, so at the LHC, but we don't find so new physics. So with this upgrade, if this upgrade continue, or would it stop at some point? So if yes, so what would be this kind of indication or reason that could make it do that? So what's the limit, more or less? What do you think? Thinking maybe FCC, I guess, or?
Okay, I mean, here it's really would become extremely speculative. I mean, my answer would be what the comment Luisa made before. Of course, one should also look at other ways of exploring structural matter and the secrets of the universe, but certainly we have a very powerful way. By the way, this is essentially, we're changing techniques and technologies, but the technique is always unchanged since more than 100 years, since Rutherford experiment to probe the structure of the atom. Okay, so we need a high energy probe to look at matter at smaller scales. Now, stepping back and looking at the evolution of science over the past 400 plus years, we should not be concerned if, even if we would end up stagnating for a couple of decades, but certainly this should not reduce the motivation to continue refining our experimental tools to go beyond.
Yes, indeed. And we have also a nice comment from Rachel Tang, so who is watching, so from Malaysia as well, having applied as a student as well to CERN. I would like now to have also Alan. So you were mentioning, speaking about the organizational way. So with the USA being observer, so do you want to come back on this question, maybe, Alan?
Well, I think it'd be more important to clear up a historic point that is my second question, with having to do with Isidore Rabi. Luciano, in your view graph, I believe you said that Isidore Rabi tabled the proposal for CERN in 1950, and then the proposal was accepted in 1951. This may be just an idiomatic point. Was Rabi in favor of CERN, or was he trying to stop it? Because the verb to table in a governance sense can mean stop it.
No, definitely Isidore Rabi was not only in favor, but was really, he devoted his energies in those years to make this happening. And I can tell you that immediately after, when the convention for the foundation of this provisional council was signed by 11 countries, the same day the letter with the signature was sent to Isidore Rabi by the provisional Secretary General, the Secretary General of this provisional organization, Eduardo Amaldi, telling Rabi, eventually, what you envision is becoming reality, and thanking him for all his
Yes.
important role in making this happening. No. I mean, of course, it was not only Isidore Rabi, but it was certainly very, very influential. And he immediately realized that UNESCO could have played a very important role in the post-war world, with science being this unifying force. And it really spent, it really elevated the science to this role of scientific diplomacy as a way as a channel to make countries to communicate and to exchange information among them. A very important role.
Yeah, it's very good. Thank you. And that your last point about science diplomacy and UNESCO leads me to ask the first question. As an observer, the U.S., I suppose, has certain responsibilities and commitments, but they're not strong. And I'm wondering how you view that relationship in terms of the overall collaboration.
So the US plays a very important role at CERN. It's a CERN observer, so directly contributes. It's not a member state, but it directly contributes to the construction of its infrastructures. But in particular, it's a very important participation in the experimental program. So you have CERN as a host lab, with a number of countries I've shown before, 24 member states, 10 associated members and 4 observers, and they contribute to the construction and of the facilities and operation of those facilities. And then you have the experimental program, and the experimental programs are open to the entire scientific community worldwide. I was showing before that we have a community with more than 17,000 users, representing over 110 nationalities. And the US groups are very strong. And, we have, if I take now as an example, the the four LHC collaborations. Now, again, I would not quote specific numbers, but certainly they are probably the largest contingent in the CMS collaboration. This is also reflected on, the spokesperson of that collaboration being several times from the US. They are very strong also in all four experiments, also in Atlas. I've been the spokesperson of the ALICE collaboration, and we have a very important ALICE US collaboration with 10, 11 institutes, national labs and universities. So I would say they play a key role in what we're doing here.
Okay, good. I'm glad you clarified that. Thank you.
And
And congratulations.
And that's very mutual. For instance, of course, Europeans have been participating steadily in the programs in the US. Now, the US is is preparing for the construction of a large facility, the Electron-Ion Collider at Brookhaven National Laboratories. And again, the European scientific community is contributing to that program. So that's why I was mentioning before, it's actually good that given also the cost of these facilities, we a little bit diversify. In Europe now we are pushing very much the very high energy frontier. In the US now there will be this new facility that will collide electron beams again into protons and heavy nuclei to understand better the structure of protons and nuclei as well. And then the entire scientific community will contribute to the experimental program at that facility.
And indeed, I would like also to add with the US LHC for the machine part. So indeed, that was one of the large contribution as well with Japan together, American and Japanese, working for those inner triplet. And I was working for 12 years, so in that direction. So it was a big involvement as well of the US in that case. So then we could potentially, so more questions from Luisa, because indeed most of us have been involved with CERN at some point or another in our life, and I think this is really the driver and the motivation, a model in many cases. So thanks also to this UNESCO model. We're speaking about the open source potentially. So again, that's also the importance as well that CERN can prevail. So this possibility for sharing and exchanging across the different laboratories with the different domain. And Luisa, indeed, with the cosmic ray as well. So I think it was a lot of development that you exchange as well. So with CERN. So with and then on the Luisa
wants to comment on that, but I just wanted to add, Christine, because I mentioned it very briefly that we very much are aligned with these goals of knowledge sharing since the very beginning. It's this is really, I think it's one of my backup slides, which really shows that it is written in our constitution that one of the goals is to share with everyone the results and the knowledge we acquire through the experiments at CERN. But these are not just empty words. I just wanted to again remark that keeping this goal in focus, CERN was developed essential tools to do that. In particular, let me mention SCOPE, which is this sponsoring consortium for open access publishing in particle physics, which is a pioneering collaboration that I would say has transformed the landscape of high energy physics journals into open access at no cost for the authors and for the users. So this is extremely important. And now, since several years, again, jointly also with UNESCO, we put in place a program which is broadening the policy also to include open software, open hardware, education, training, and outreach.
Indeed, the outreach.
The SCOPE consortium actually was not only pioneering for particle physics, it has been adopted for all sorts of publications everywhere now. So it was really the beginning of the enterprise. And at the beginning, nobody was believing on this model because people were scared about double payment, from the funding agencies and the universities. And so everyone was very suspicious. And in the end, it was the right way to go. And what the journals have now, which is called transformative agreements, are just copies of the SCOPE consortiums opened and developed at CERN many, many years ago. I don't remember when, at least 10 years ago. Do you remember?
Yeah.
At least. So it was.
It's longer ago now. I don't have the exact
So it
date
was
on.
a primacy also for this, due to CERN.
Very good. So, and we have as well an invitee here with Paola Catapano. So, Luisa, so you have been also from the beginning of this Physics Matter, so presenting, so how everything has been possible. And I just wanted to give her the possibility to finalize as well this session. So with how we
She's on the boat again. She's on the boat.
I'm teleworking from my boat. I'm sorry. I needed to do the wintering very urgently. I couldn't sail as much as I could, and I needed to come because Luciano held me in Geneva to help with the 70th anniversary events. So that's why I'm on my boat now. In the winter, it's snowing outside, and it's 4 degrees inside. That's why I'm wearing my hat. I'm really sorry to join in these conditions, but I'm working. I'm teleworking essentially. So I don't know why Christine wanted me to join. Luciano is much more in a position to represent the CERN 70th than myself. But yes, I'm glad to join you and Luisa, surely, because we've been together since the beginning of these seminars, and I will be pleased to join again with my future projects.
Exactly. This is why we wanted to finish as well on how we started as well 4 years ago with the Polar Quest. So I think that was important to have also the Navy as well on board.
Thank you.
To complement this expedition. And indeed, so far, the event in October and November as well. So we have been, so the pleasure to have, so you as well sharing some of the session for the introduction. That was the full event organized with Luciano. So I think it was really good to hear you also on the stage also at that time in October.
Thank you.
Thank you so much for connecting.
Well,
and
for those who are connected and who don't know Paola Catapano, she is one of the leaders of the science communication at CERN. And as you can see, it's multitasking. It's not simply
there is common ground.
Carry on adventures related to particles, and you report. And this is the way to do it, because one should never be locked in a lab. You have to be open door.
No, but I'm doing science from my boat as well. So yes, of course. There is a lot of need of data and ground truthing for any sciences, but in particular oceanography and climate sciences. And that's going to be my commitments for the future years.
Exactly. And this is those applications that I like as well, the possibility for CERN to look at those different spin-offs. So how to apply that as well, high energy physics with societal challenge. And so I think that we wanted maybe then to finish on those positive note as well, looking at everything that so Luciano had brought over those 70 years. Great summary. And we could have then possibility to contact as well Luciano later on as needed, and we will have so the presentation. I will share then just my screen now to speak about the last presentation of the year, which will happen to be in December 12. So we will have then Thanksgiving next week. Then after that, so the presentation of technically, so looking more at the technology that can happen as well, thanks to physics as well, with Malik Maza. So directly as well from South Africa. And it will be much more information as well, maybe connecting so the Sustainable Development Goal as we had presenting them last month with some application to medical as well, looking at those nanotechnologies. I think it will be a very interesting presentation as well on the 12th of December. So we will then finish on this happy note and get possibility to thanks again, Sir Luciano, for having possibility to summarize all of that. A great pleasure to have you here. So thank you very much. Thank you to everyone. And let's stay tuned.
Bye.
Bye. Bye-bye, everyone.